So this is a short discussion of the material in section 4.1, and it's about finding extreme points on a closed or on an interval. And we're going to use the derivative. You know, we've studied derivatives and how to find derivatives, and so now we're going to use them to find extreme points, and then we're going to actually eventually use them in optimization problems later on in the course. So let's just look at this one picture right here. So it's this one right here. And we see this graph. And I think we can just see that, there's certain points that are like the point B comma f of B. That's the highest point on the graph. And we see that the point A comma f of A is the lowest point on the graph. But if you look at C here, like this point C right here, you see that's called a local minimum. So if you actually look just a little bit to the left of C or a little bit to the right of C, those points, the second coordinates are greater than f of C. But of course, they're if you go out far enough, you're going to find points that are where the second coordinate is smaller than f of C. But near x equal to C, f of C is a local minimum. Okay, so let's just talk about a few definitions here, though. We don't actually have to know the exact definition, certainly just have some kind of intuitive sense of, what's the difference between absolute and local minimum or relative minimum. Okay, so let's say we have some kind of interval, and if f of c is greater than f of x for every x in the interval, then f of x is the absolute maximum. So in other words, f of c, that second coordinate, f of c is the highest, the largest second coordinate on the interval, if we actually look at the graph. And then we can just flip that around. If f of c is less than or equal to f of x for every x in the interval, then f of x is called the absolute minimum, or the smallest point. And we're going to have word problems later on where we're trying to find the absolute minimum and the absolute maximum. Okay, so now how do we find these points? How do we find the point C where we have an absolute minimum or absolute maximum? So we're actually going to look at the derivative. Okay, so one thing we know about the derivative, right? So when the derivative is zero, that might mean that there's a change. So when the derivative is zero, right, we have this tangent line. Let's see if I can draw this. Not great, but the tangent line, when f of x, when the derivative is zero, the tangent line is horizontal. And so we could potentially have a change in direction in the graph of the function. It doesn't have to be, but like in this case there, so we see at B, the graph is going up for x less than B, right? The graph is going up for x less than B, and then the graph goes goes down for x greater than B. So one of our strategies for finding the absolute minimum or maximum is to find where the derivative is zero. And on the other points of interest, maybe the derivative is not even defined. Okay, so let's just look right here. Let's see if I can draw this right here. So let's say we have an absolute value function. So we see that the absolute minimum occurs at that peak that kind of looks like a V, so like at the vertex there. Okay, so the absolute value, the derivative is not defined at that sharp change in direction. So let's say this is just some point x equal to c. So the derivative doesn't exist at x equal to c. It exists to the left of c and exists for x greater than c, but doesn't actually exist at c, because all of a sudden you have this, to the left of c, the derivative is negative, and to the right of c, the derivative is positive. So when we're looking for these absolute minimum, we're going to find what are called critical points. And so the two things we have to remember is that a critical point is where the derivative is zero or where the derivative isn't defined. Okay, so here I have an example I've taken from the homework. Let's just talk about this a little bit more. Okay, so one of the things that you'll see in the homework is, just find the critical points for a function. And so in most cases, it's rare that we, at least for this course, you don't see too many problems where the derivative isn't defined. Usually it's not defined, or where the denominator might be zero, or you have an absolute value function. But here, so problem A right here, yeah, so it's just a polynomial. So of course, polynomials, the derivative is defined everywhere. So just take the derivative. So the derivative of x to the fourth minus 8x squared. Take the derivative. So we have 4x cubed minus 16x, and then just fully factor. And we see the critical points occur at x equals 0, x equals -2, and x equals 2. So these 3 points are where the derivative is 0. So if you actually graph that function, that's where you might get a change in direction of the graph. And we're going to learn a little bit later on that just because the derivative is 0 doesn't mean that there's a change in direction in the graph. It might be what's called an inflection point. We have to look at the secondary. We'll talk about that later on. And here's just another example, which I'll let you read that yourself. And I have one example from the homework. Okay, so we're going to talk about extreme values. So that's basically it says it refers to the function values or basically the second coordinate. So there's this one theorem here if you actually are interested in math or being a math major. So if f is continuous on a closed interval a b, then f actually has an absolute minimum or an absolute maximum on that interval. Okay, so so there's two type of extreme values that we're going to be talking about. There's the absolute minimum, and we talked about this a little bit before, and then there's the relative minimum. Okay, so the absolute minimum is that you're if you look at on an interval, it's actually the second coordinate is the largest value, or the second coordinate is the absolute smallest value. Where relative just means that nearby, you're the absolute, you're the largest or the smallest. Let's just look at these few examples right here. So this one clearly here. So this one, okay, so if you look at the endpoints, like this endpoint right here, that's the absolute maximum right here. And so this actually could be, and this would be the absolute minimum right here, right? There's no point, if you look at the second coordinate doesn't go, the graph doesn't go down any further than that. And okay, so now let's just look at another one here. So, well here, this nice example right here, it's not, there's a hole in the function. So there is no absolute minimum. So that extreme value theorem says the function has to be continuous on a closed interval for it to have just an absolute minimum and an absolute maximum. But the absolute minimum doesn't occur because the function is not continuous. But of course, this point right here is the absolute maximum. So here, this function here, this is defined on an open interval. So if you actually, so there is no absolute minimum or maximum. So no matter what point you pick, because you can't get to the endpoint, you can't choose the absolute minimum or the absolute maximum for this example right here. And here you have just a straight line, the closed segment a comma b, and the graph here. This is the line y equal L, right? So the absolute minimum and maximum are both equal to L. Okay, so now let's just look at, so I think we have an idea of what the absolute minimum is, the highest point or the lowest point. And then there's also, we're going to talk about relative minimum or relative maximum in the open interval. Okay, so once again, it's the same thing. So when we talk about relative minimum, we're talking about in the open interval. And again, and they occur at the critical points. So, and again, so relative minimum just means that, here, let's just go back all the way up here. I was going to draw something, but maybe I'm not going to press my luck. Okay, so again, this point right here, this point C right here. Let's see if I can erase this without causing a big mess. Yeah, so this point C, that's a relative minimum. You go a little bit to the right or a little bit to the left of C. The points to the right of C, the second coordinates are greater than f of C. You go to the left of C, the second coordinates are greater than C. But I mean, if you go out far enough, you're going to find points where the second coordinate is smaller than f of C. That's why we say it's relative. So near x equal to C, that's the smallest point. But it's not the absolute smallest point on the, it's not the absolute minimum on the graph. So let's just go back down here. Okay, so relative minimums, yeah, once again, we just find the critical points. We have to calculate the derivative and then solve f of x equals 0, or where f of x is undefined. And then here it says learn in the future. Yeah, so that eventually we're going to need to look at the second derivative, but right now we're going to skip that. And also now so the relative minimum, we look in the open interval and we just look for the critical points. Now for the absolute extreme right here, we're going to consider the endpoints. You just kind of create a table. You find the critical points, and also you identify the endpoints and just make a table and then look at the values of f of x and you see where is the function, because now we're trying to find the absolute minimum and absolute maximum. So you find all the critical points, you consider the endpoints, make a table, and then you just see where the second coordinate is the largest or the smallest. So actually, here's an example right here, but I'm going to skip this. I'll let you read this. And I actually have this, this example, hopefully right here from the homework. It's really not too bad of a problem. So, so this is problem, It says 16. Okay, so let's see. I might have labeled it 8. Okay, 16. Okay, so I'll relabel that. Okay, so says determine the location and value of the absolute extreme points of f on the given interval if they exist. So one thing is I graphed, and it doesn't hurt to graph just to kind of give you an idea of whether your answer is right. I mean, you have the I think it's a good idea to graph, right? We don't want to be disconnected from the algebra and all the calculus and from what the graph actually looks like. But we do have to use, but I'm going to ask you to use calculus in your answers. We can't rely on looking at the graph for the absolute minimum or the absolute maximum. Okay, so here's our function, 5 cosine squared of x, and on the closed interval 0 pi. And we want to find the absolute extreme values. Okay, so let's just use our, the rules that we learned. So remember, for the absolute minimum or the absolute maximum, we find the critical points, and we also identify the endpoints. We evaluate the function at the critical points and the endpoints, and we see which is the biggest and which is the smallest. And then from our theorem, this is a continuous function, right? We actually graph 5 cosine squared x. It passes what I call we can graph it without picking up our pencil test. Okay, so we're not actually going to prove that it's continuous, but it's defined on this closed interval. So yeah, there's that theorem that says that a continuous function has an absolute minimum and an absolute minimum and absolute maximum on a closed interval. So there is an absolute minimum and absolute maximum on the interval from 0 to the closed interval from 0 to pi. So first, let's just use so we're going to use calculus to solve this. Okay, so let's just take the derivative of, so we're going to look for the critical points. Now, the derivative is actually defined anywhere where there's no actually sharp points. And again, so for this course, the only place you're likely to see a function where the derivative doesn't exist, where there's an absolute value involved, or maybe where the denominator is 0. Like the derivative of the square root of x, right? So x equal to 0, the derivative isn't defined. Okay, so okay, even though the function is defined as 0. Okay, so let's take the derivative of 5 cosine squared of x. Okay, and so it turns out, okay, we're just going to use the chain rule. So 2 times 5 times cosine of x, and the derivative of cosine of x is minus sine of x. So here we have, here's the derivative. And instead of multiplying that out to be minus 10, I'm going to use one of my favorite identities in the world. 2 sine of x cosine of x is equal to sine 2x. I think for this course, that's one of the more useful identities. And also the one for cosine 2x, we'll see later on, that's a pretty useful. There's a few versions of cosine of 2x, but we'll get to that when we need it. But yeah, so when you see sine of x cosine of x, I recommend just trying to convert it to sine 2x. Maybe it'll help you. Okay, so now, and this will help us, we have to solve sine of 2x equals 0, right? Because remember, what we're doing here is we're trying to find the absolute minimum, absolute maximum of 5 cosine squared x on the closed interval from 0 to pi. And so the derivative turns out to be minus 5 sine 2x. So we don't care so much about the negative 5. All we care about is where sine of 2x is equal to 0, because that's the derivative of cosine squared x. Okay, or that's the part of the derivative of cosine squared x that we have to worry about for finding the critical points. Okay, so we're gonna first, let's see if we can find where the derivatives are on the open interval. So the sine function is 0 the sine function is 0 at x equal to 0 and x equal to pi. And I can even write that in. And then, and so we're going to solve 2x equals 0 and 2x equals pi. So we get x equals 0 and x equals pi over 2. And we want to make sure that, we're in the right part of the domain, because we're only considering from 0 to pi. And so the period of sine of 2x is pi, right? That we learned that earlier this year, that it's the period of the sine function is 2 pi over, whatever that number is there, right there, which is 2, so it's pi. Okay, so sine of 2x is 0, so we can just add, so we have these two solutions, x equals 0 and x equals pi over 2, and we can just add k pi to each of them, where k is an integer. So sine of 2x is 0 when x is equal to, a multiple of pi, or when x is equal to pi over 2 plus some multiple of pi. Okay, so the only solution in 0 to pi is x is equal to pi over 2. Okay, so now so let's just look at the critical points and the endpoints. There's only one critical point. So this is the only critical point. That's the only critical point. Okay, so that's the only place where the derivative is 0 in the open interval from 0 to pi. And so now we want the absolute minimum, the absolute maximum. So we're going to look at the endpoints. Right? So here's our interval, here's our closed interval. So the endpoints are 0 and pi. And then plus we have our critical point of pi over 2. And so we're going to evaluate the function. Right? So cosine of 0 is 1. So you just square it, you get 1. So and then you multiply it by 5, you get 5. Cosine of negative 1, and because cosine of pi is negative 1, and you square it once again, you get 1. Multiplied by 5, you get 5. And cosine of pi over 2, that's the first coordinate, right? So remember, cosine is the first coordinate. When you rotate around pi over 2 units or radians. And so, so cosine of pi over 2 is 0. Okay, so clearly x at 0 and pi are the absolute maximum, and pi over 2, x equal pi over 2, the absolute minimum occurs at x equal to pi over 2. Okay, so the absolute maximum, so I'm actually going to write out, so the absolute minimum, I know I'm trying to write on the screen, occurs at 0, what did I say? I'm sorry, absolute maximum. I'm sorry, absolute maximum. And it's 0, 5, and pi, 5. And the minimum, and it's pi over 2, 0. And that actually corresponds to our graph. I can make this go up, right? That kind of corresponds to our graph, maximum, maximum, minimum. And for this function, we can kind of use some of our common sense, is that, well, cosine squared, it's got to be, the smallest possible value you could have is 0, right? You square something, it can't be negative. And we know that, that cosine of pi over 2 is 0. So we know the minimum, the smallest second coordinate has to be 0. Okay, so this is a relatively, as far as trig functions go, usually some of the harder problems with finding the absolute minimum, maximum involve trigonometry. So this is maybe one of the easier ones. I was trying to find one that involved trig. But okay, so that's all for now.